Welcome everybody to my talk called Taking Static Type Safety to the Next Level, Physical Units for Matrices. My name is Daniel Withopf. I'm an engineer at the German car supplier Bosch, and I work on automated driving, self-driving vehicles, and driver assistance. And while doing that, over the last years, I implemented a library called TypeSafe Matrix that I want to present to you today. If you have questions, feel free to ask them in the Zoom webinar. I'll answer them towards the end or maybe also in the middle of the talk. So let's see what's in it for you today. As the title of the talk mentions, of course, we're mainly going to talk about physical units in vectors and matrices. But even if this topic is not that interesting for you, I think there's a lot that you can take home today and learn about static type safety in C++ and library interface design. We're going to learn what I consider the ultimate goal in library interface design, which is if it compiles, it works. So we'll learn how to design a library that works whenever it compiles. So we'll try to fix all bugs or detect all bugs at compile time as much as possible. So what does that mean in practice? Throughout the talk and in the library, I followed a few overarching design principles. First of all, I'm trying to anticipate problematic usages and prevent them at compile time whenever possible. This will go so far that it almost feels like a static analyzer built into your C++ type system. So it's effectively your math and physics teacher built into the C++ type system. Furthermore, my goal is to enable users to make sweeping changes that work once they compile again. So this means when you do changes in your library, ideally you get static assertions that alert you of all the problems in your library or in your code where you use the library. You can fix the problems, and once it compiles, it's very likely that everything is correct. Of course, there's no guarantee, but at least it's very, very likely. And last but not least, my goal was to make the user code as expressive as possible. This means that ideally, you should be able to tell from a single line of code what is going on in that code line. For example, if you do a code review, it's really nice if you can see all the relevant information on the code line that you're currently reviewing. And you don't have to go to other code lines. Before we dive into the details, I want to start a little bit with the terminology and background that we need for the talk. If you haven't heard about physical units libraries or haven't used them, that's not a big issue. You can simply think of them as being strong C++ types that behave as you would expect. So for example, if you have a physical quantity of meters, then you can add a second physical quantity that also has a physical unit of meters to the first quantity. You cannot add two physical quantities with a unit of meters and seconds because the units do not match up. And you also can multiply any two physical units with each other and get a valid physical unit as a result. If you want more background info, please check out P1935. That was written by Matthias Pusch. That is intended for C++ 26 now, and also his library on GitHub, or one of the excellent talks from earlier C++ conferences. So there he talks about how you can use physical units libraries to annotate scalars, so integrals or floating point values with their physical units. And what I'm dealing with today in my talk is how we can use these physical units annotations in multi-dimensional vectors and matrices. So now I want to move on to the terminology that I'm using during my talk. So in classical linear algebra, you have vectors and matrices. So in a linear algebra library like Eigen, for example, there are vectors, which would be anything that's n by 1 dimensional, and matrices are everything that's n by m dimensional, so truly two-dimensional. In classical math, however, the terminology is a little bit different. In classical math, you have a point in a vector space, and there are also displacement vectors. So displacement vectors are the connection between 2 points in such a vector space. And of course, there are also matrices and also different kinds of matrices, for example, covariance matrices, Jacobians, and a few other types. And in my library, TypeSafe Matrix, I also make that distinction between a point. In my library, a point gets a vector tag. We will see that later, how this is done exactly. But just keep in mind, a point gets a vector tag, and the displacement vector, so proper vector in the mathematical sense, gets a delta vector tag in my library. And of course, I also have several different matrix types that will also be annotated in the type itself. We will see later on what the full taxonomy of these types looks like. Now I want to move on to the actual task that we want to solve in this talk today. So we want to combine linear algebra library types with physical units, meaning we want to put physical units inside vectors and matrices. So as I mentioned, for physical units, there's P1935, the library. For linear algebra, there's, for example, Eigen, or also a proposal for the standard library called P1385 by Guy Davison and Bob Stiegel. Now here's a code example how you can use these two libraries. In the first code line, we're creating a physical quantity with a dimension of length and a unit of meter. This is done with this code line. And the second code line now creates a three-dimensional vector with a scalar type of double. And we just use 1, 2, 3 as the values in that three-dimensional vector. And now the key question is, how can we combine these two libraries? So how can we put a physical unit inside a vector? In such a simple case, where we just want to use a single physical unit inside a vector, so we want to have a three-dimensional vector with a unit of meters, that's still fairly easy, as is shown here. So we can simply create such an FS vector here. And as the value type, we no longer use a double now, but instead we use a physical quantity with a unit of meters. And if both libraries are designed in the right way, then this works out of the box. It does for these two libraries. And now we can create two vectors, v and u, and we initialize these with 1, 2, 3 meters and the other one with 3, 2, 1 meters in the individual elements. And now we can add these vectors together, v and u here. It's a valid operation, so this will compile. And as an output, we get the result of 4 meters in each of the entries. So this is fairly easy if we have the same physical unit in all entries. But now the question is, what happens if we want to have different physical units in each of these entries? To see that in more detail, I want to explain you about an example that's from my application, but maybe you have something similar in your application. So in this example here, we want to track a vehicle in one dimension. And in this case, we would like to check the distance in meters, the velocity in meters per second, and the acceleration in meters per second square. Now, when we want to do that, we can simply create such a three-dimensional FS vector. We initialize it with 1 meter, 2 meters per second, and 3 meters per second square. Now, the only thing that's remaining, the only question that's remaining is what should we use as the value type here? Because we're now using 3 different strong types. As I mentioned, physical units are different types in all C++ physical units libraries. So we have 3 different distinct types. So there's no longer a unique value type that we could use for that FS vector here. Now, question for you that you can maybe try to answer in your head. Which C++ data type can we use to represent this? So we want to have different types that we store in such a linear algebra vector. If you've worked with C++ for a while, there are a few types that might come to your mind. So first option would be a tuple, of course. You could use a tuple that can store different types inside each of the elements. Or the second option would be a state variant. That's, of course, also possible. I'm not sure if you immediately see it. For me, it's fairly clear that this would lead to very, very complex code. If you have a variant, you would have to visit each element, which makes your code really, really complex. And for a tuple, it can also become really complex, as we will see on the next slide. So in this example, I want to take a look at a bigger matrix. So here we have a 4x4 matrix. In this example, covariance matrix, for example. And that 4x4 matrix now has 16 entries, of course. And this can now have up to 16 distinct physical unit types. And that's a fairly small matrix. We could even have like 10 by 10, 20 by 20 matrices, which would mean up to 400 distinct types for each of the units in the elements. And I guess you can already see that this would sort of like increase the complexity a lot. So if you want to use a variant or a tuple with 400 elements, that blows up the compile time a lot. So I don't think this is feasible. And we'll also see in the next part of the slide why there's a much simpler solution. There is a much simpler solution because the physical units in each of the entries of a matrix are not completely independent. The unit structure in these matrices is a little bit simpler. So the only thing that can vary are the row units and the column units. So if you have 4 row units for such a 4x4 matrix and 4 column units, this is sufficient to describe all multipliable or meaningful matrices that are annotated with physical units. It's actually a result from the book here by George W. Hart called Multidimensional Analysis that dates back from the 90s. This is one of the only materials that I could discover on the topic, and I only discovered it after I was finished with my work, so it's fairly difficult to find. But he showed, George W. Hart showed, that all meaningful or all multipliable matrices have to have such a unit structure. And this means that we no longer need a tuple sort of with 16 elements here, but we only have to annotate a matrix with 4 row units and 4 column units. And then the individual units of an element here are given by a combination of the respective row and column units. We'll see later what the combination means. So it can either be multiplication or division usually. Now I want to go back a little bit and explain how I started my work on the topic. So my main motivation was started when I worked with classical linear algebra libraries like Eigen. So in that example, you might have a code line like this here, where you access vector B at index 3, and then you assign that value to vector A at index 2. Now, when I read a code line like this in a code review, it's often fairly unclear to me what this code line really does. There are usually 2 questions that come to my mind. First of all, what do the individual vector entries describe? Because there's no description here what's at index 3 in vector B or at index 2 in vector A. Could be anything. Second of all, this could also be an out-of-bounds access, because we don't know that the vectors are actually at least of dimension 2 and 3. They could be smaller than that. This gets especially complicated if you don't have a fixed constant here, but if you would access with runtime indices. Now maybe in the next try, the creator of that code rewrote the code a little bit, and it now looks like this. So now we're accessing vector B at position X index, and we're assigning it to vector A at velocity X index. Now, when you see code like this, there are again 2 questions that you have to ask yourself. First of all, have the right index constants for the respective vector type been used? Because there's no guarantee that position X and velocity X are actually meant for vector B and vector A. They might just be enumerator constants that are meant for completely different vectors. That's also possible. Second question, is assigning a position to a velocity really intended? Most likely a physics teacher would intervene here because we're assigning 2 values with incompatible physical units. So most likely this is a bug in your code because you're assigning a position to velocity. And the last try, maybe the code line now looks like this here. So we're now accessing vector B with velocity X index and assigning it to vector A, again at velocity X index. Now this code line looks better because now the indices seem to mean the same thing. So they seem to have the same semantic meaning. But there's still one last question remaining. Namely, in which coordinate frame are vector A and vector B? Because it might just be the case that vector B is from one coordinate frame and vector A is from a completely different coordinate frame. And if these 2 coordinate frames do not overlap, then this might again be an invalid operation because the coordinate frames are not compatible. So from that, I came up with my linear algebra library wish list. So a wish list of what I would like to have in an ideal linear algebra library for my application. First of all, I would like to have a protection against out-of-bounds accesses at compile time, which means that it's guaranteed that you can no longer access an element of a vector out of bounds and run into undefined behavior. This would be really nice. Second property that I would like to have expressive and enforced names for all vector and matrix entries. If we go back to the previous slide, this means that you can no longer access vector at index 2. Instead, you always have to mention an enumerator constant or a tag type. We will see later how it's solved exactly. You always have to mention a name type that gives you an indication of what is actually the content of that index in a vector. Furthermore, I would also like to get support for non-uniform physical units in vectors and matrices. As we've seen before, This is an important application, so it's not sufficient to just have uniform vectors where all entries have the same physical unit, but we also want to represent non-uniform vectors and matrices. And furthermore, I would also like to have a physical units check for all matrix operations, again, at compile time. This means that the physical units in the elements of the vector have to match up. As we will see in this talk, this is not the best condition that we can have. There are much stronger conditions that we can actually enforce. And we'll see later on in the talk how this is done. And last but not least, I would also like to have coordinate frame annotation for all vectors, matrices, and transformations. So this means we can annotate a vector that it lies in a certain coordinate frame A. We can annotate another frame that it lies in a coordinate frame B. And we can also annotate transformations that the transformation transforms from coordinate frame A to coordinate frame B. This would also be a really, really nice property that's usually useful when you code with linear algebra code. Good, so let's move on to the solution space. The first ingredient that we need for a solution is what I call named index structs. These named index structs identify each index with a unique name. In this first example here, the struct dxc, that stands for distance x Cartesian, identifies an index, so Cartesian x position. And this index is created by deriving from a base class and specifying 3 template arguments. First template argument is the coordinate frame in which this index lives. So in this example, it would be a vehicle front axle coordinate frame. If you're doing self-driving, programming self-driving vehicles, then this would be the front axle frame of the ego vehicle, for example. Then we specify that this is the Cartesian x-axis in that frame. So this is the axis identifier. And last but not least, we specify that this index has a physical unit of meters. And there's also a second example. If you're going to create a different index, this here is a dy sensor. This is the y position index or y distance index in sensor frame. Down at the bottom, you can also see how such a coordinate frame is created. This is simply an almost empty struct that derives from a base class. And we specify whether that coordinate frame is moving with respect to the Earth, which we assume is fixed, or not. We will see later on in the talk why this information is needed. Now, onto the general rule, how I created these indices. So these indices consist of 3 parts. First part is the physical quantity. That would be distance, velocity, acceleration. So I abbreviated that with D, V, and A. The second part describes the axis, x, y, z axis. And the last part describes the coordinate frame in which we are. In this example here, this would be the sensor frame. Now I should also explain why that dx index here does not mention the coordinate frame. This is just a convention in our application, as that vehicle front axle coordinate frame was sort of the standard frame in our project. We have to use these indices fairly often, so we left out the name in that one index struct. But of course, as these are just simple structs, everything here is completely configurable by the user. So you could replace all these names with different names or come up with a different naming scheme. All of that is possible. That's sort of the configuration that comes on top of my library. Now I want to show the first type and also the most important type that is part of the library. It's named the same as the library itself. So it's called type-safe matrix. And that class has 4 template arguments. First template argument is the scalar type. So do we want to use a float, double, or some integral value as representation type inside the matrix? The second argument is the row index list. So simply a type list that contains the indices that I showed on the previous slide. And the third argument is the column index list. So again, a list of indices that describe the columns in such a matrix. And the last template argument, fairly important, is a matrix tag. And this matrix tag is used to distinguish between different types of vectors and matrices. So for example, we distinguish between covariance matrices, as I said, Jacobian matrices, there are information matrices, different kinds of vectors. I will later on show the full taxonomy of all different types. And I forgot to mention the only member in that class is a matrix of an underlying linear algebra library. So in this example, it's eigen. I also have an implementation for Blaze available, so you can pick one. And in this example, that eigenmatrix gets the same scalar type as the class typesafe matrix, and we use the size of the row index list and column index list as the size of the underlying matrix. Should be fairly obvious. Now we can create our first type alias to make usage a little bit easier. So this here is a typesafe vector. And that's simply a typesafe matrix with a given scalar type, row index list, and matrix tag. The only thing that's special here is that we use a type list with a no index type as column indices. This is sort of an empty index type that does not influence the physical units in such a vector or matrix. Because in a vector, you only have the rows which influence the physical unit, and the column is just, a no-op sort of in the index space. And then last but not least, we can create a position vector, 3-dimensional in vehicle frame here, another alias, and that's a typesafe vector with a given scalar type. And we use a type list, as I mentioned, of the indices, dx, dy, and dz that I showed earlier. The tag that we're using here, the matrix tag, is a vector tag. So as I explained earlier, that would be a point in the mathematical sense. If we would use a delta vector tag here, it would be a displacement vector in the mathematical sense. Now, I want to move on and show you how you can create a vector and access its elements. Here in the first example, we're creating such a 3-dimensional position vector in vehicle frame. And we now have 3 different ways how we can list the individual elements. The first and most type-safe way how we can initialize an element is to call the entry method on another vector. And here we simply specify, okay, we want to have the dx index from this vector. And then it's also automatically assigned to the first entry in the vector we're constructing, which again has to describe that dx index. Otherwise, the user would get a static assertion. So here, as I explained, there's a full check. So other position has to contain that dx entry. The current vector we're constructing has to contain this entry or this index as the first element. And the 2 vectors also have to have the exact same matrix tag or vector type. The second option that's a little bit less type safe is to use the method rep coefficient si to create an entry. So we again have to mention the index here. That would be dyc in that case. And we simply pass a physical unit argument to that method. So in this case, we want to create a physical quantity of 1 meter and assign it to that index dy in that vector. And the last and least type-safe version that we can use is to use a TSM rep coefficient, rep coef, without the SI, and then we can simply pass a plain scalar argument, so double or floating point, whatever the underlying type is. In this case, a double. And it should be obvious here that there's no physical units check at all. So this method should be avoided as much as possible. It's better to use the other 2 if you want to have full type safety. So the last method here is maybe useful if you want to set an element to 0 or to 1, then it might make sense to use that. Otherwise, we usually avoid it. Now, in addition to create a construction of a vector, there's also the possibility to read and write from existing vectors. So again, we have 3 different versions. The first one is the most type-safe one. In this example, we're calling the entry method to read from one vector. We've seen that before in the construction. And then we call the assign entry method to assign this entry to the exact same entry in the vector where we're calling assign entry on. And again, this is the 3-star type-safe version. So we have a full check here. We check that that entry is actually part of other position. Assign entry verifies that this index is part of position vehicle. And if any of these conditions wouldn't be fulfilled, the user gets a static assertion. Second most type-safe version is to use coefficient si for reading and coefficient si ref for writing to an entry in a vector matrix. This assigns physical units, and I also want to mention why we have 2 different methods here. As I do not store the actual physical units in my vectors and matrices, I'm only storing plain scalars. I cannot return a reference here with a method that accesses the SI unit, so I need a proxy type here on the left-hand side that we can assign to. And last but not least, again, least type-safe version is to use the add method, or maybe I should mention in the previous code line here, we could, with that physical unit aware method, we could assign a Y position in one frame to an X position in a different frame. So the physical unit matches up, but they still have a semantically different meaning. And here, with that add method, in the last example here, we can even assign a velocity, Y velocity in center frame to an X position in a completely different frame. So again, a very questionable operation. And we should avoid this operation as much as possible. Now, there are also more complex ways how we can create a vector or matrix. In this example here, we're creating a delta position vector of dimension 3 in center frame, so a different frame. And this can be done by initializing the first two elements here with the multiplication of a duration in seconds with the first two elements of a velocity vector in the same frame. So we're multiplying a duration in seconds with a velocity in hopefully meters per second, which gives us a displacement in meters. And this displacement vector, two-dimensional displacement vector, can now be used to initialize the first two elements in our three-dimensional vector. Now what's missing, as I mentioned, is the last entry in that vector. We only initialized the first two. So we've also have to list the third element in the vector. And this is done here by calling the entry method again and accessing the DZ sensor index from another vector. The same thing, of course, also generalizes to matrices. So far, we've only seen how we can create vectors. But the exact same thing is possible for matrices. So here we're creating a covariance matrix, which now has two proper type lists. So the type lists contain X position and X velocity in a frame, and are both identical. Now, the individual elements that we have to list here in a matrix, of course, we have to list two indices because we now want to describe the row and column inside the matrix that such an entry describes. So here in that example, I'm just calling rep coefficient SI 4 times. But of course, there are also other options. You can use the methods that I introduced before, the entry method or the rep coefficient method is also. Now, in addition to these simple examples here, there are also more complex ways how we can construct a matrix. For example, we can construct it from 4 columns. We can construct it from 4 rows. We can construct it from 4 individual blocks, or we can construct it from 3 rows and 3 smaller blocks for the last row. All of this is possible. So this might seem here, especially the matrix example, might seem a little bit complex, the syntax, because you have to mention so many indices here. But this is also one of the main features and advantages of such a library. You always have to mention the indices you're constructing. This means, as an example, I did that once. If you want to exchange the order of the indices in your vector or matrix, you can do that. You simply would exchange the indices here in the definition of that matrix. But then when you do that, you will get several static assertions because your indices or your entries here are no longer listed in the correct order. So I'm expecting row major order, row-wise listing of the elements. And if the elements are not listed in the correct order, then the user gets a static assertion from the library. And this means when you exchange the order in the vectors and matrices, you have lots of static assertions, and then you have to fix all the static assertions to get it to compile again. When you're finished with that, there's almost a guarantee that your code works again and has no bugs left over because everything with respect to the index order is checked at compile time in the library. So there's no way how we can mix up the order of the indices. You always have to mention the indices, and the library is able to detect if you mix up the indices. So I think this is a nice example of what we had in the beginning. If it compiles, it works. Back to our slogan from the beginning. We'll get back to that a few times during the talk. So now I want to show what happens when we access an element inside a matrix, especially how we can infer the physical unit that we get in such a case. So on the left-hand side, the black code box shows the full definition of the matrix. That's probably not that important. You can also look at the graph I made or the table I made on the upper right part. So here, the Jacobian matrix, we're creating a Jacobian matrix, and the Jacobian matrix contains mesh dr, which is a radial distance measurement, for example, from a radar sensor in meters. The second row contains the radial velocity, mesh vr, in unit meters per second. And the last row contains the measured angle in radians to, I don't know, the next vehicle next to us from a radar sensor. The columns of that matrix are fairly easy. The 3 columns simply describe the X, Y, and Z position in our vehicle frame. And now the question for you, maybe we don't have a poll today, but maybe you can try to answer it for yourself. The question is, which physical unit should be returned when we execute code line like here? So we're accessing the Jacobian at the index mesh vr and dy. This is also shown on the right-hand side. So we're accessing the row mesh vr with a unit of meters per second and the column dy with a unit of meters. Now, you might know that Jacobians sort of describe the derivative or describe derivatives. So what we put in a Jacobian matrix is the derivative of the row index with respect to the column index. And now this might already give you a clue about what the correct result is in that case, or what should the correct result be in that case. So we're having a derivative, and you might know from math that derivatives can be approximated with a finite difference quotient. So we're dividing when we're calculating a derivative. This means that in this case, we simply have to divide the 2 entries here. So we divide meters per seconds by meters. So the meter falls out, and we end up with 1 divided by second as a unit for this entry. And it turns out that this can be generalized to all different types of vectors and matrices if we introduce the notion of row exponent and column exponent. So in a Jacobian matrix, we would have a row exponent of 1, column exponent of -1. It's also shown here. The row exponent is 1, column exponent is -1. And now we can come up with a general rule of how we can infer the physical unit of an entry. We simply have to take the physical unit of the row. So this is here meters per second. We raise it to the power of the row exponent. Row exponent is 1, as we mentioned. And then we multiply it with the column unit, meters, raised to the power of the column exponent, which is -1 in this case, meaning we're in the end dividing meters per second by meters. And then we end up with 1 divided by second. Now the slide shows the full taxonomy, as I promised, of all different vector and matrix types that can be used inside my library. And I think it's also all mathematically meaningful types of vectors and matrices. First block here are proper matrices. So as I mentioned, we have covariance matrices, Jacobian matrices, and information matrices. These are the inverse of covariance matrices, which you can also see from the row and column exponents here. They are the sign inverse of the exponents in the covariance matrix. The next block here, so these were the matrix type. The next block describes vector types. So as I mentioned, we have position vectors, points in the mathematical sense. We have displacement vectors that get a delta vector tag, and also information vectors, which have the physical unit of their indices inverted. And last but not least, there's also what I call vector collection. This might be new for you. These are matrices dimension-wise, so they're actually 2-dimensional, but semantically, the content of these vector collections are vectors. So for example, if I have a matrix with n position vectors in its columns, then I would call that a position vector collection, because it's semantically not a proper matrix. We have to observe different calculation rules. If we have vectors, semantic vectors in the columns, then when it would be a covariance matrix, for example. So as I mentioned, we have a position vector collection, displacement vector collection, and information vector collection. And of course, there are also transposed versions of all of these vectors and matrices. I didn't list them here, but it should be fairly obvious what the exponents are in that case. Simply exchange row and column exponent. So until now, we've achieved unit-safe element access and out-of-bounds protection. This was sort of the first half of my talk. Now the question is, can we achieve even more than that? And it turns out there's a lot more that we can achieve. We can almost try to represent the whole mathematical problem space inside such a library and sort of enforce the mathematical calculation rules that are usually valid for vectors and matrices. So let's see if unit safety, plain unit safety is enough. To see if this is enough, let's try to be unit safe for all operations on vectors and matrices. So first example of an operation that I want to look at with you is this one here. So we have an operation where we add two vectors, and the first vector here on the left-hand side describes X and Y position in vehicle frame, and all the entries have a physical unit of meters. The second vector here on the right-hand side has indices that describe the X and Y velocity in the same frame with a physical unit of meters. So what do you think? Should this be a valid operation? So I guess usually when I ask that question, it's fairly obvious. So I guess you can guess the answer. So we're adding two vectors with incompatible physical units here. We're trying to add meters to meters per second. So it should be fairly obvious that this is an invalid operation. And of course, the operation is forbidden by my library. So this would lead to a static assertion. But now let's move on to a slightly more complex example. Should this operation here be allowed when we're adding a vector, two-dimensional vector that has a unit of meter in all of its entry to a delta or displacement vector? The delta symbol here stands for displacement vector that again has a physical unit of meters. So the question was, should this operation be allowed here? And I'm going to answer for you. It might seem, okay, I'm already seeing an answer in the chat. That's really nice. So it seems to be sensible to allow us the answer. And yes, that's also usually the correct answer. But in this case, it's a bit more complex. That was a little bit a trick question from my side. So you're right. In general, this seems like a valid operation. In most cases, it is valid. But what if we have a special case here? So if we're actually adding a position vector that describes X and Y position in one frame, and we're adding a displacement vector that describes Y and Z position in the same frame. In that case, these vectors describe semantically different things, which means they should not be added together or addable. The library should prevent that because the index types do not match up. And this is sort of the main lesson that we should take home from this slide. Unit safety is not enough. We actually need index type safety, which is a much stronger condition than just physical unit safety, type safety. Good, so I think that's another really nice example from the slogan from the beginning. I also have it here. If it compiles, it works, our ultimate goal for library interface design. We're preventing all the invalid or at least questionable operations. In earlier versions of my talk, I also had the question whether it would make sense to maybe extend these two vectors that we're adding here to three-dimensional vectors. So we sort of invent this Z coordinate in the left-hand side vector and the X coordinate in the right-hand side vector, and set both to 0. But I think it makes much more sense to simply prevent this operation and not have anything happening under the hood underneath. Good. Now I want to show how a pretty complex operation inside the library works out. I want to visualize that and also explain all the checks that are done when such an operation is executed. So here we're doing a matrix multiplication. So we're taking a covariance matrix in vehicle frame. We're multiplying it from the left-hand side with a Jacobian and from the right-hand side with a Jacobian transposed to end up with a covariance in a center frame. Now what happens here is also shown on the slide. So in the middle, we have our covariance, the Jacobian transposed on the right-hand side. And now there's a check that the indices in these orange boxes here, so the column indexes from the middle and the row indices from the right-hand side, actually are identical, and that their row and column exponents are the sign inverse of each other. And only if this is possible, if this is the case, then this operation is valid, and we will end up with the column indices from the right-hand side that now move over to the covariance in the middle. So the inner indices sort of cancel out, similar to the dimensions in a classical matrix multiplication, where the dimensions cancel out. Here, the indices cancel out, and then we're doing the same thing on the left-hand side. We're verifying that the indices in these orange boxes are identical. Exponents are the sign inverse of each other. And if this is true, the row indices from the left-hand side are moved over to the covariance in the middle. And now we can see we end up with a covariance in center frame. Up here, I ran out of space, so these are also indices in center frame. And as we can see, This is also what we're assigning it to in our code line. So we're assigning that to covariance and center frame, which means the operation is valid here and it compiles. In all other cases, if any of these types would be different, or if we would try to multiply to covariance matrices or something like that, then the user would get a static assertion and be alerted of the problem because it's mathematically incorrect what he's trying to do. So here I want to show what the addition operator in class typesafe matrix looks like. So for that addition, we take an argument that's derived from matrix base. So that's the base class for all the operations in the library. And we're returning a matrix expression. And that's such a matrix expression describes the result of the operation. That's similar to what Eigen does to get expression templates. So I'm also using a similar mechanism in my library. The two template arguments for such a matrix expression are, first of all, a promotion type, in this case, promotion to the addition. And this type is responsible for promoting the types inside my library. So it's basically specifying what the return type of this addition should look like by inferring the four template arguments of class typesafe matrix. And the second part of that matrix expression, so the second template argument for that class, is simply the decal type of the addition of the two underlying linear algebra libraries. So this forwards sort of to Eigen and returns whatever Eigen returns when you call the addition operator. So the first template argument is responsible for the promotion at compile time. And the second argument is responsible for doing all the calculations at runtime. But this is sort of outsourced to the underlying linear algebra library. So I'm simply forwarding this type here. Now I want to show what such a promotion looks like. So the promotion to the addition we've seen earlier. This is an almost empty struct that inherits from a few what I call require space classes. So we require identical scalar types for the two arguments. So for the one we are calling the addition operator on and the argument to the addition. And this also injects the scalar type of our resulting typesafe matrix into this promotion. Then we require identical row and column indices. Of course, if we add two vectors, the row and column indices should be identical. Then we're also requiring identical row and column unit exponents. So they have to be identical. And yeah, you might be confused why it might seem a little bit complicated. We could just require that the matrix tag is identical. But as I mentioned, we're distinguishing between points and displacement vectors, which is why it's a little bit more complicated. And this is also shown by the last condition here. We require that the matrix tags are addition compatible. So what this means is, for example, that you can add a displacement vector to a point, but you cannot add 2 points. You can subtract 2 points and get a displacement vector. That's also possible. Or you can add 2 displacement vectors, but you cannot add 2 points in the mathematical sense. Now, last but not least, I want to show how that requires identical row indices type looks like. This is again an almost empty type. The only content is a static assertion that checks that the row index list of the two types is identical. And if they are not identical, a static assertion is fired. And as I mentioned, this also injects the row index list into the resulting type. So on the next slide, all of this here, it might seem fairly complex, but all of this serves a purpose. I should mention my library has been designed for C++11. So this is sort of the best way what you can do in C++11 to get really nice template error messages. I will show that on the next slide. So here we're adding a 3-dimensional vector to a 2-dimensional vector. And this now shows what the error messages look like in that case. First of all, we get a static assertion from the type identity checker that we've seen on the previous slide. Then, if we continue in the instantiation history, we can see that this originates from promotion to the addition. So this came when we executed an addition operation. And we can also see that requires identical row indices failed because the row indices in that addition are not identical. Last but not least, we can see from type identity checker instantiation that the two index lists here, the row index lists, are not identical, which is the cause for the compilation error. Now, if this all seems fairly familiar, we have C++20 by now. So of course, as I mentioned in C++11, it's not possible to do it in a different way. but with C++20, it would be much better to implement that with concepts. I did a small implementation here for that addition example, and we implemented the logic with concepts. And you can see you get a nice error message, and you also have modeled it in the proper way in the concept space. So you would again see, okay, here's a static assertion because two types, the row index lists are not identical. I don't want to go into details here. Yeah, if you're interested, you can check it out afterwards. Good. Now we've concentrated a lot on like sort of the implementation details far down inside the library. Now I want to zoom out a little bit and explain a little bit about the big picture, so what we've actually achieved so far. So this slide, the image on the right-hand side is actually taken from the book I mentioned, Multidimensional Analysis by George W. Hart. In that slide, oh, sorry, I have to go back one slide. In that slide, I want to explain the difference between the two approaches that I mentioned. So in the beginning, we had that uniform matrix approach where we simply captured or used the value type in a vector to specify a physical unit for all of the entries in that vector matrix. Of course, that can only represent uniform matrices where all entries have the same unit. With my design in type-safe matrix, we can also represent non-uniform units in vectors and matrices. And this is visualized here on the right-hand side. So the uniform matrices are simply the orange array here in the middle that can be represented with a uniform matrix approach. And with type-safe matrix, we can represent the blue oval here of multipliable matrices, which is a much bigger problem class than what we could model before. And now I want to show that even inside that gray area here, we're able to model the problem in much more detail with type-safe matrix and prevent lots of invalid operations that cannot be prevented with the other approach. To see that, let's see what we can add and multiply in such a library. So here, we first want to take a look at the addition of two vectors, A and B. Different options that we have here is an XY point in vehicle frame, and YZ point in the same frame. We have a displacement vector XY in the same frame, and we also have a velocity vector Vx and Vy in the same frame. As you can see from the table here, the only thing that we can prevent with such an approach is when we when we add vectors with incompatible dimensions. So anything that's marked gray here, there we're adding meters to meters per second. And of course, this can be prevented because this annotation is available. But for all the other vectors, there's no way how we can prevent this operation. So we cannot prevent adding XY position to YZ position because the annotation is simply not available with that approach. With type-safe matrix, on the other hand, most of the table here already turns to gray. So as we can see, we cannot add 2 points, even if they have the same indices. That's what I mentioned earlier. We also cannot add 2 points if they have different indices. What we can do is add an XY point to an XY displacement vector or 2 XY displacement vectors. That's all possible. And all the other operations here are grayed out because they are invalid and most likely a bug, which can be detected when you use such a library. Now I want to show the same thing for multiplication of two matrices, A and B. So here we're looking at Jacobian matrices, transposed Jacobians, covariances, and vectors. And when we only have a single physical unit as an annotation for the whole matrix or vector, then all of these multiplications are valid. As I mentioned earlier, you can multiply any 2 physical units and get a valid physical unit as a result. And this is exactly what happens here. If the dimensions of the matrices match up, there is a valid physical unit that you get as a result, and you simply create a matrix with the appropriate dimensions and the matching physical unit. And this is the correct return type here. So all of these operations would compile in that case. With type-safe matrix, on the other hand, situation looks a lot different, and most of the table turns to gray. So what we can multiply is 2 Jacobians, given that the indices match up, of course. So that's why I put a maybe here. So if the indices match up and the dimensions match up, then you can multiply 2 Jacobians. You can also multiply a Jacobian from the left-hand side with a covariance on the right-hand side. This is what I've shown earlier in the large example that we looked at. You can also multiply Jacobian with a vector, or to transpose Jacobians if the indices match up, or covariance with a Jacobian transposed from the right-hand side. All of this is possible. So it should be fairly obvious that, yeah, even already from the colors here, you can see that by using type-safe matrix, we can prevent many, many incorrect usages. So all of these gray areas here are bugs in your code waiting to happen. And it's really difficult to discover them if you don't have the annotations and cannot alert the user at compile time. Good. So I think, again, this is a nice example of the slogan from the beginning. If it compiles, it works. And now I see a brief question in the chat. Are the categories, the question is, are the categories D for distance, V for velocity, and A for acceleration hard-coded in the library? Or would it be possible to use or to specify an arbitrary list of types, energy, entropy, temperature? Yes, it's of course possible to specify these. Distance, velocity, acceleration have a few special properties that we will see later on, because they are Cartesian indices that can be transformed to different coordinate frame. But other than that, you can freely define your indices. That's of course possible. Yeah. Time's already a little bit running up, so I think I'll briefly skip over transformation and rotation matrices. So just so much, it's also possible to specify transformations between different coordinates frames with a library. That would be an isometry in that case. And you specify source and destination frame, the dimension, and then you can transform from a position in one frame with a transform that goes from odom to vehicle frame to get to position in vehicle frame. This is possible. And again, there are several checks. So you cannot transform velocities because you should only rotate them and not translate them. You have to use the linear part. Yeah, I'll simply skip over the rest here. You can watch any of my earlier talks that are longer if you want to know the details about that. Good. So far, we've mainly approached our slogan, if it compiles, it works, from the mathematical point of view and physical point of view. So we've tried to prevent misusages where the math is actually incorrect or the physical units are incorrect. But of course, we are C++ programmers, so there are more reasons why a program can fail. So there are also C++ related reasons why you can run into problems or even produce bugs. The question here, what are the most common bugs when using a C++ linear algebra library? So I'll answer that quickly here to not use too much time. So there are two, well, fairly common ways how you can produce a bug, at least what I observed. So the first one is you can have aliasing. So if you have a left-hand side and right-hand side of an equation, if the right-hand side overlaps with the left-hand side, then you can get incorrect results. Or you can also have dangling references in your vectors and matrices. I will show how this can happen and also how this can be prevented now. So here, this is again an eigen example. So let's assume we have an eigen method, calculate offset, that returns an eigenvector 3D by value. Then we have a pre-existing vector A, also from eigen, and we now add these two vectors together, and we calculate the norm, so the length of the resulting vector. This is a completely legal operation in eigen. Everything is okay if you do it like that. But there's one small thing that I can change, which makes this immediately undefined behavior. If we split that code here into two separate lines, so we first calculate the sum here, and then we calculate the norm of such a sum method, then this will immediately lead to a dangling reference. Not sure if you're aware of that, but eigen does not actually calculate the result here when you do an addition. It merely creates an expression object that describes how this can be calculated when it's actually needed. And this means that such an expression object stores its argument usually by reference if it's a proper vector or matrix. And now you might already be on to the solution here. So I mentioned this stores the arguments by reference, the sum type here that we get as a result. And as I mentioned earlier, calculate offset returns by value, meaning we are storing a reference to a temporary, and on the next code line, this reference is already invalid, and we get a dangling reference, undefined behavior in this case. The same would also happen if we capture that some variable by reference. That leads to exactly the same problem. Now I want to show how we can prevent the usage of such, or how we can prevent this problem. The idea here is to prevent the usage of such a matrix expression as an L value. So whenever we have a named variable that contains such a matrix expression, and we want to call a method on that, this is something that we can prevent. This example here, again, I'm showing the addition operator. And to implement our check, we now need two overloads of that addition operator. We need the first overload, which is the L value overload here, and the second overload, which is the R value reference qualified overload. And now in the L value reference qualified method, we simply verify that the argument that we're calling that method on is not an L value matrix expression. If it would be, then we fire a static assertion and the user is alert of the problem. Second thing that we have to do, we now also have to check that the argument that we are passing to that addition, so the second argument of the addition, also is not an L value matrix expression. This can again be done with a simple helper method. And again, if it would be the case, we fire a static assertion. And last but not least, we simply execute the addition in the underlying linear algebra library. And again, as I think from the beginning, mentioned in the beginning, this is a nice example of if it compiles, it works. So we're trying to prevent all the bugs that we can imagine. Good. That already leads me just on time, I think, to the conclusion. What have we achieved so far in the talk? We've seen that we can achieve full support for physical units in vectors and matrices. This means we have expressive and enforced names for all vector and matrix entries. So we always have to use these index types, and it's no longer possible to access with an integer index. We also achieved the protection against out-of-bound accesses at compile time because we use these indices. And it's fairly easy to verify that the index is actually part of the type list of our matrix or vector. We've also seen that we have constructed a proper taxonomy or a full domain model for linear algebra types. So we've learned that there are covariance matrices, Jacobians, and in the library, there's also an encoding of which operations are actually meaningful and mathematically correct for these types. Furthermore, we have a compatibility check for index structs and matrix types for all linear algebra operations, and even a bit more than just the index struct check. As I mentioned, we're doing a lot more checks. Furthermore, we also have achieved the built-in coordinate frame tagging. That was the part that I had to skip over a little bit in the end, the transformations, but I think you got the drill. And we are also able to prevent dangling reference bugs. And what I also am able to prevent is the aliasing that didn't fit in today's talk. So if you want to know details here, you can check my talk from CPP Now this year, so 2022, where I explained all the checks that I implemented. And to conclude my talk, last but not least, what we started with, I think all of that is a really nice example of that slogan from the beginning: if it compiles, it works. Now, I should mention, we at Bosch in Germany are hiring. There's also a site in Plymouth in Michigan. If you're interested in self-driving vehicle or automated driving or driver assistance, please check out the linked job postings. And all that remains for me now is to say thank you very much for listening. I'm really looking forward to your questions. Maybe the check host can help me out and tell me if we still have time for questions. If not, feel free to join me in the Q&A session afterwards in GatherTown. Yeah, I think we still have one question from the chat, whether it's also possible to use other SI units, kilograms, ampere, radian, steroradian, or even British imperial units. That would be also possible, but in my library design, I usually refrain from mixing up different unit systems. So if you want to have that, then it might be more complex. So usually it helps to stick with one system. Of course, the underlying physical units library that you use will support operations like that. But if you really want to have conversions, I don't think it's a good idea to have that done implicitly in a linear algebra library. You might offer something explicitly where the user has to request it. That might make sense, but doing it implicitly for a 100 by 100 matrix might incur runtime overhead that you don't want to have, or at least you want to see it explicitly. There's one more question. Is there anything that seemed like a good idea at the start, but was later abandoned? Yeah, I did several rewrites of the whole library. I didn't end up like immediately with that solution. It took a lot of experimenting. The first thing that took me quite a while to figure out is how the units are inferred in matrices, so that there are Jacobians, covariance matrices, and how the units are inferred. That took a long time. So I didn't like change everything completely, but what happened is that I added a lot of stuff afterwards. I solidified the internal design, and I also added a few things one after the other. For example, the entry method in the beginning that was added later on. All of the checks regarding dangling references and aliasing protection is also something that I added fairly recently. So yeah, but other than that, I don't think I hit a complete dead end where I had to go back from and completely do everything differently. So good, I would say that's it. Time is up for now. If you have more questions, as I said, I will check the chat in Discord. I will be in the Q&A session afterwards. So thank you everybody again for listening, and hope to talk to you later or another day in the conference.